Good morning. Today's lesson is going to focus on chemical equilibrium. We will learn in this lesson how to set up the equilibrium expression for both homogeneous and heterogeneous reactions. We will look at what the value for K means as far as the extent to which the reaction progresses. We will learn how to calculate the value for K and how to manipulate the value for K under changing reactions. Chemical equilibrium is defined as the point where the forward rate of the reaction is equal to the reverse rate of the reaction. In this example that you see here to the right, we have N2 plus 3H2 forming 2NH3. When we have equilibrium being established, that does not mean that the concentrations are all equal, but we have the concentrations remaining constant for both the reactants and products over time. On the molecular level, we still have the reaction taking place where we have N2 molecules reacting with H2 molecules forming NH3, but it's just that the breakdown of the NH3 molecules is occurring at the exact same rate that the formation of the NH3 molecules is taking place. The graph that you see here where we're looking at the changes in concentration versus time, you can see for your N2 and your H2, just like we talked about with our kinetics unit, is always going to decrease its initial concentration, and the NH3 is always going to increase its concentration as the reaction progresses. The focus that you will see for equilibrium is on the right side of that dashed line. Hopefully you remember from our previous unit that when we're looking at the very initial pieces of the reaction puzzle, at the time t equals 0 or very close to that, this side of the graph is related to the kinetics of the reaction. And then once the concentrations level out, that's where we look at the equilibrium. So when we look at the equilibrium reactions, all reactions are reversible under suitable conditions. They will reach a state of equilibrium. This term reversible just means that the products can go back and reform the reactants. We show this in the balanced equation by representing it with a double-sided arrow. That way we know that we have both the forward and the reverse reactions taking place. When we reach equilibrium, the concentration of the products and the reactants are no longer changing because the rate of the forward and the rate of the reverse reactions are equal to each other. So chemical equilibrium is a dynamic state because the reactions continue to occur, but because they occur at the same rate, it appears as if nothing is taking place. In this diagram, we are going to see how the changes in the concentration progress over time for a reaction to take place. You'll notice here on the very far left, you have a very faint brown color to the gas. And then as you go progressively longer through time and we get further and further to the right, you'll notice that the intensity of the brown color will be increasing. And so that will allow us to know that the NO2 is becoming more prominent in that reaction vessel until the point where you can see in the final picture the color of the brown gas appears to be the same. And so we can assume at that point that no further change is taking place under that set of conditions. And so we now have reached equilibrium. So if we look at that previous reaction, we have N2O4 as a gas breaking down into two molecules of NO2. At equilibrium, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. If you recall from our kinetics, we would write the forward reaction just as we see N2O4 going to two molecules of NO2. If we were to write the rate expression, we would say the rate, and I'm just going to say for that forward reaction, would be equal to some value K times the concentration of N2O4. We can assume that this is an elementary step for a reaction, so we can use the coefficients for the orders. And then if I were going to write the reverse reaction, I would have 2NO2 going to N2O4. And I could write the rate for the reverse reaction being equal to K times NO2 concentration squared. Now, since we know that at equilibrium, the rate of the forward and the rate of the reverse reactions are equivalent to each other, I can therefore take these two quantities and set them equal to each other. So I would know at equilibrium that I could say that the K for the forward direction times the N2O4 equals the K for the reverse direction times the NO2 concentration squared. If I put the K's together on the same side, I would have K for the forward reaction divided by the K for the reverse reaction equals the concentration of NO2 squared over the concentration of N2O4. Now, the ratio of your K to the forward reaction divided by K to the reverse reaction, remember these are not equivalent to each other because they're opposite processes, we can set this equal to our arbitrary K value. So that would give us an expression that we could use for this reaction of K, which is a capital K, equals the concentration of NO2 squared over the concentration of N2O4. Now, I just want to take a moment and stress one thing. Throughout the next 8 weeks, you're going to see a lot of different variations of K. They all mean the same thing as far as the setup is concerned. When we look at the K, this is just a generic K. It can be K, it can be KEQ. When we look specifically at concentrations, we list it as KC. If we're looking at a completely gaseous system in terms of their partial pressures, then we look at it in terms of KP. When we talk acids and bases, you'll see a Ka, a Kb, and a Kw. When we talk insoluble salts, we're going to see a KSP. The setup and the parameters are all the same. It's just looking at a specific type of reaction that's taking place. So please don't get confused by any of the different little subscripts that you're going to see with these Ks. In general, for any reaction that is at equilibrium, we can set up our expression for K by placing the concentration of the products raised to the power of their coefficients divided by the concentration of the reactants raised to their coefficients. So for that value K, product concentration raised to the power of their coefficients divided by the reactant concentration raised to the power of their coefficients. So if we look at this generic reaction, Ja plus Kb forms Lc plus Md. I can take my two products, C and D, raise them to the powers of their coefficient. So C would be L, D would be M. A and B, again, reactants, they're in the denominator. We raise to the power of their coefficients, J and K. When we look at the value for K, K will always be the same for a given temperature regardless of the amount of reactants or products that are present initially. The system will always react in a way that will reestablish the same ratio of reactants to products to allow the value for K to be the same. So again, K will only change with temperature. So you can have millions of equilibrium positions for a particular reaction if it is done at a specific temperature. So what does the value for K tell us? K reflects a ratio of the product concentrations to the reactant concentrations for a reaction. So as a result, the K will indicate the extent to which the reaction progresses in the forward direction and will tell us how much product will form at a given temperature. When we look at the value for K, if we have a small value for K, and typically when we talk about this, that small value, we're representing K being less than 0.01. That will indicate that we have very little product that has been created before it reaches equilibrium, so therefore the reaction will favor the reactants. So when we talk about that favoring the reactants, that just simply means that at equilibrium, there will be a much greater amount of reactant than product molecules. When we talk about a large value for K, Typically, we're talking about K being greater than 100. That will mean that the reaction is going to progress very far towards the product side, and you'll have very little reactant that is remaining. So we say that this reaction will favor the products, and therefore at equilibrium, we would have more product molecules found than reactant molecules. We could also have another situation where K is close to 1, and that would basically represent the fact that you have fairly equal concentrations of reactants and products once equilibrium has been established. Now, the values for K, do not get scared when you're working these problems. You can have your K values being extremely large or extremely small. I've seen Ks that are as low as 10 to the negative 70th power, and I've seen Ks as large as 10 to the 44th power. So you can see large amounts or very small amounts for K. That does not mean that you've done anything wrong with your work. So hopefully this diagram will give you a sense of what we're talking about with the reactants or products favored within a chemical reaction. So in this first example, letter A, you can see we have the blue colored molecules being the reactants. We have the red representing the products. So in this equilibrium mixture, you can see that the vast majority of the molecules that are present are reactants, and you have only one that is a product. So when we look at that reaction, we have 1 over 49, assuming that there are 50 molecules present inside of that vessel. We have one reactant or one product molecule. We have 49 reactant molecules, and so that gives us a value for K of approximately 0.02, reactant favored. In our second example, we have the orange colored molecules converting into a greenish color. You'll notice now I have only one reactant molecule that's left, and I have a large percentage of product molecules. So in this situation, you can hopefully see that this would be a product favored reaction, and we have a K value that is equal to 49. And in our last example, now I have an even split. I have 25 molecules for the gray colored molecule, and I have 25 of the green colored molecules. So I have an equal ratio, and so as a result, we know that we have an even split with our K equaling 1. So neither reactants nor products are favored. So now let's look at how we set up our equilibrium expressions. Anytime that you are asked to set up an equilibrium expression, we're just simply writing K is equal to, again, the products raised to the power of their coefficients divided by the reactants raised to the power of their coefficients. So when we have a homogeneous equilibria, that means that the reactants and products are all found in the same phase. So when we look at setting up the equilibrium expressions, we only focus on things where we can have a change in concentration. So we focus on gases and aqueous systems. Anything that is a solid or a liquid will not be included in the equilibrium expression because their density is essentially their concentration, mass divided by volume. And as a result, we know that solids and liquids both cannot be compressed, so we cannot change their concentrations. So therefore, their values are just incorporated into the equilibrium constant for a particular reaction. So whenever you see those in the expression, you can just cancel them off and get rid of them and just include the things that are either gaseous or aqueous in your expression. So let's look at a few examples here, how we would set them up. So for our first example, the N2 plus the 3H2 forms 2NH3. We would simply write the K is equal to the concentration of NH3, concentration squared, divided by the N2 concentration, and it has a coefficient of 1, so I'll leave it. And then I have H2, it's got a coefficient of 3, so we'll cube that value. So that would be my equilibrium expression. You just simply write the substances and what powers they're being raised to. You do not put any numbers into them for the expression. For our second example of a homogeneous equilibria, we have HCN aqueous going to H plus aqueous and Cn minus aqueous. So for this one, I would have K equaling the concentration of H plus times the concentration of Cn minus and dividing by the concentration of HCN. Every one of them has a coefficient of 1, so therefore they're just raised to the first power. So now let's look at our heterogeneous equilibrium. So in these instances, again, anything that is a solid or a liquid, we will eliminate from the equilibrium expression. So for this first example, I would have my K being equal to the concentration of O2 raised to the third power. In my second example, I have water as a liquid going to 2H2 as a gas plus O2 as a gas. So for this example, my K would be equal to the H2 concentration squared times the O2 concentration. Okay, so let's look at an example problem over the next few slides and learn how to calculate the value for K. So when we look at an equilibrium expression, hopefully you can notice again, because I have gas, gas, and gas, I have a homogeneous system. When we look at the gaseous systems, we can either treat them as a concentration, in which we would use the brackets, or we could solve for Kp instead, and that would be dealing with the partial pressures for each of the gases. So when we do the Kp for a particular reaction, we use parentheses instead of brackets. So just remember, parentheses, partial pressures, both start with a P, so those go together. The system is set up the exact same way, products over reactants, but instead of the brackets that we would use for the concentration, so we could label this as a Kc, we would use the Kp, and we would have the parentheses for the partial pressures. One other note, under most circumstances, Kc and Kp will be a different value. We will learn how to calculate and interconvert between the two momentarily. So now let's look at how we would plug in our values at equilibrium to determine the value for K. So again, for this expression, we have partial pressure, so I'm going to use the Kp version. So I'd have the partial pressure of NH3 squared divided by the partial pressure of N2 and the partial pressure of H2 quantity cubed. So I have my values for each of the each of the equilibrium pressures for our reactants and products. So I just plug that into my expression. So I'd have Kp is equal to the partial pressure of the NH3, which is 2.9 times 10 to the minus 2 squared, divided by 8.9 times 10 to the minus 1 to the first power, and 2.9 times 10 to the negative third to the third power. So when I plug all those into my calculator, we end up with a Kp equaling approximately 3.9 times 10 to the fourth. So in this situation, almost 39,000. So you could say that there will be a large proportion of NH3 molecules present in that equilibrium mix compared to the N2 or the H2. So now we can look at the relationship between Kp and Kc. So when we have a reaction, if we're given the Kp for a gaseous system, we can simply set it up where the Kp times the RT raised to the negative delta N, this is coming from the ideal gas law, PV equals nRT, will allow us to determine the Kc for a reaction. And conversely, if we have the Kc for the reaction, we can solve for Kp by taking the Kc and multiplying by R and T and raising it to the positive delta N. For this reaction, the delta N is the sum of the coefficients of the gaseous products minus the gaseous reactants. The R value is 0.08206 or 0.0821 liter atmospheres per mole Kelvin, and then the T is your temperature in Kelvin. So we will look at that last example where we had our Kp equaling 3.9 times 10 to the fourth power, and we'll convert that into Kc. So I would take the Kp value and multiply that times the R and T, and we'll just assume that that temperature that we had for that last reaction, we'll just do it as 298 Kelvin, and then we have our negative delta N. For our reaction, again, we had N2 plus 3H2 forms 2NH3, so my delta N would be equal to 2 minus 4, or a negative 2. So 1 plus 3 gives me the 4. So reactants is 4, products 2. So 2 minus 4 gives me a negative 2. So I would take my value, 3.9 times 10 to the 4th, multiply that times 0.08206 times 298 Kelvin, and we're going to raise that to the negative 2. So if we plug that in, 0.08206 times 298, and we raise that to the negative 2 and multiply it by 3.9 times 10 to the 4th power, and our Kc would be equal to 65.2. So a much different value that we get, much smaller in magnitude, but still showing that the products are favored for the reaction. So we're going to now look at the ways how we can manipulate the value for K by changing the direction in which the reaction is moving. So when we look at a reaction, the opposite direction is always just going to be the inverse of the value for the K. I will show you this using this example that we have here. If you notice, it says for the reaction N2 plus O2 forming 2NO that is run at 25 degrees Celsius, the Kc is 1 times 10 to the negative 30th. Use the information to write the equilibrium constant expression and calculate the equilibrium constant for the reaction 2NO yields N2 plus O2. So I hope that you can recognize if we treat this as the forward direction, and you notice the bottom, I have my product, the 2NO, now becoming my reactants. So this is the reverse reaction for this top reaction. So if I were to write my K for the forward direction, I would have the concentration of NO squared divided by the concentration of N2 and the concentration of O2. If I do that for the reverse reaction, I would have the concentration of N2 times the concentration of O2 divided by the concentration of NO concentration squared. So you'll notice that all I've done is taking the inverse of that forward reaction, flip their directions there, and that gives me my K value for the products. So when I actually do my calculation, I can take the K for that reverse reaction. That is going to be equal to 1 divided by 1 times 10 to the negative 30th power. So I would know in this case that the K for the reverse reaction would be 1 times 10 to the positive 30th. K is a unitless value, so I would just leave it as is until you get to probably graduate level chemistry. We're going to now look at the next couple of manipulations of K, the first of which involves a multi-step reaction. The overall reaction will be the sum of 2 or more individual reactions, and the value for K for the overall reaction will be the different values for K multiplied together. The second example that we would have would be if in that multi-step reaction we have to multiply an individual reaction by a set of whole numbers for the coefficients, we would raise the power of the K to that change in the coefficients. So if we look at a example here where you have HF plus yields H plus F minus, and H2C2O4 breaks down into 2H plus C2O4 2 minus. Each one of those individual reactions has a Kc value that is associated with it. However, when you notice for the overall reaction, we have 2HF plus C2O4 2 minus forms 2F minus plus the H2C2O4. Hopefully you notice that for this reaction to occur, I have a coefficient of 2, for the HF, whereas my first reaction, I only have 1 for its coefficient. So as a result of that, I'm going to multiply this whole entire reaction by 2. When I do that, that would mean that I'm going to take this value for the Kc for that HF dissociation, and I'm going to raise it to that power. So I would square that value, and that would give me a new value for this particular reaction of 4.62 times 10 to the negative 7th power. I have the H2C2O4. Now notice with this reaction, the H2C2O4 is a reactant in the individual step. In the overall reaction, however, it's a product. So in this case, I'm going to have to flip the direction of this reaction, which means that I would take this reaction and I would take the inverse of it. So if I do that, 3.8 times 10 to the negative 6th, and take the inverse of that, that will equal 2.63 times 10 to the 5th power. So in order to figure out my K for the overall reaction, I'm just going to say that this is my K1 and this is my K2. So I'm just going to multiply those values together. And so my K for the overall reaction would be equal to 4.62 times 10 to the minus 7th multiplied by 2.63 times 10 to the positive 5th. And when we do that, that gives us an overall K that would be equal to 0.122. Okay, so let's just work through a couple of example problems here to finish up for today. So the first part, we want to write the equilibrium expressions for the Kc for the following reactions. So again, notice here I have an A, gas, and a liquid. So I would ignore the liquid from my expression. So the Kc for this particular reaction would be the concentration of CO raised to the first power divided by the concentration of CO2 and the concentration of H2. For my second example, I have SnO2 as a solid. So again, I can get rid of the SnO2 plus the 2CO forms Sn as a solid. Again, I can remove that, and 2CO2. So for my expression here, my Kc would be equal to the concentration of CO2 squared divided by the concentration of CO concentration squared. And finally for C, when added to Fe3O4 as a solid in a closed container, which of one of the following substances would allow the equilibrium to be established in this reaction? So I have 3 Fe as a solid plus 4 H2O as a gas, forming Fe3O4 as a solid plus H2. So just remember, the forward rate of the reaction equals the reverse rate of the reaction once equilibrium is established. So at this point, if I'm only adding the Fe3O4 as a solid, notice that is my product in this reaction. So if I were to add any of the following, either H2O or the Fe as a solid, nothing would occur, because in order for a reaction to take place, the Fe3O4 must react with the H2. So the only substance that would allow the equilibrium to become established would be the H2. Okay, so we're going to look at one last example problem, and we're going to look at the equilibrium mixture between sulfur trioxide, SO3, and SO2 plus O2 gas. So we have a balanced chemical equation. So just for practice, if we are going to write out the Kp expression, we would see the partial pressure of SO2 squared times the partial pressure of O2 divided by the partial pressure of SO3 squared. And for this, again, remember parentheses for the partial pressures. Now, in order to solve this problem, however, this is a conversion between Kp and Kc. So hopefully you remember we'd have the Kp value is equal to Kc times the RT raised to the delta N. So the delta N, again, number of gaseous moles of products minus the number of gaseous moles of reactants. So I have 2 plus 1, so I have 3 moles of gaseous products, and I have 2 moles of gaseous reactants. So my delta N would equal 3 minus 2, or 1. So when I set this up to solve for Kp, I would have my Kc 4.08 times 10 to the negative third multiplied by 0.08206 and multiplied by 1000 Kelvin, and we're raising that to the first power. So if I multiply all that out together, we end up with a Kp of 0.335. All right, so you guys have some practice problems that I would like you to work on. Tomorrow we will do a little bit of practice and focus on the reaction quotient, which is looking at the non-equilibrium systems in order to predict the direction that the reaction will shift. Have a lovely afternoon and come with questions tomorrow.